2, 1. I got 2116. 210. We'll just go with what you have. And this is moles of pH3 phosphate. All right. Next, we have to figure out how much phosphine can be formed from the amount of hydrogen that we have. So 83 liters. Now, some of y'all might be thinking, let me use the ideal gas equation, right? You're totally right, but there's a faster way to do this. And what is that way?
Divide by 22.
Yeah, so we know that the volume of a gas at STP only is 22.4 times the amount of moles. All right, so we can just rearrange this equation because we're looking for N. So we would get the amount of moles of hydrogen gas is equal to the volume of hydrogen gas divided by 22.4, like Cash Max said. All right, so 83 liters H2 divided by 22.4 liters per mole at STP, right? This is only because they gave us the conditions of STP in the problem. So 83 divided by 22.4 equals 3.705. And this is going to be moles of hydrogen gas. And we know for every 6 moles of H2, and this is from the balanced chemical equation, 4 moles of phosphine are produced. So times 4 divided by 6, 2.47 moles of phosphine are produced from that much hydrogen gas. So which one's the limiting reactant?
Oh, the
Phosphorus, right? Phosphorus is our limiting reactant. So like we always do, you don't have to, but I would cross all this out just because I don't want to accidentally, maybe I decide to skip the question or whatever for whatever reason and come back and use the wrong one. So you don't want to do that. Now from here, it's just, this is stuff we've been doing since basic chem, right? We just multiply by the molar mass. When we have moles, we use the molar mass to get grams. In 1.2108 times 33.97. 40 grams or 40.1. Yeah, we'll do 3 seconds. 40.1 grams of pH3 is to be produced from that amount or from this reaction. This is the theoretical yield. We all good? Sweet. All right. Number 29 says aluminum reacts with excess HCl to form aqueous aluminum chloride. How do we know aluminum chloride is aqueous?
That's not soluble.
It's soluble, right? Yeah, it's a soluble salt. So we know that they're not. Okay, I didn't start recording. Anyway, yeah, so they're just not messing with their brains. And this reacts with 35 or so it forms 35.8 milliliters of hydrogen gas over water at 27 degrees Celsius and a total pressure of 751 millimeters of mercury. How many grams of aluminum reacted in this case? And I gave you the information because I had forgotten to type it out when I made this problem.
It's okay.
Thanks. But the partial pressure of water at 27 degrees Celsius is 26.8 millimeters of mercury. So I'll give you 2.5 minutes. Raise your hand if you have no idea what you're doing. All right. Okay. All right, so. Dalton's law of partial pressure is what you have to use here. And this tells us that the total pressure is 751 millimeters of mercury. But that, because of Dalton's law of partial pressure, we can say that the pressure of water, because it tells us that it's collected over water, which tells us there's going to be some water in this total pressure. And so it encompasses the pressure of the water and the pressure of the hydrogen gas. So what Dalton's law of partial pressure says, the total pressure equals the pressure of H2, which is what we're looking for. And that's added to the pressure of water that is just existing. We don't care about it. It's just there and there's nothing we can do about it, but we can work around it. So we are given the total pressure, which is 751 millimeters of mercury. And we were not given the pressure of H2 because that's what we're actually going to look for. Because the thing is, how many, well, why am I looking for the pressure of H2?
Total pressure 751. They want us to subtract that.
Yeah, but they're asking us about how many grams of aluminum reacted, which means they're asking how much aluminum was there that reacted in this reaction. So why do I care about H2?
They converted.
Yeah, right, because we know that aluminum reacted with, and I probably should have started with this first, I'm sorry. Aluminum reacted with HCl to produce aluminum chloride and hydrogen gas. And balancing this, we'll get
2, 6, 2, 3.
2, 6, 2, 3.
Yeah.
So if we could get the amount of hydrogen gas in moles, then we can easily convert that to how much aluminum we started with. So the reason I'm looking for the amount of hydrogen gas to begin with is because I can use some equation, one of our ideal or one of our gas laws, to find how many moles of hydrogen gas we have. And because they gave us temperature and
And you don't care about aluminum chloride because it's aqueous, right?
aluminum, no, yeah, it's not a gas. Yeah, yeah. So that's why I'm looking for the partial pressure of H2. So this is equal to 2 plus the 26.8 millimeters of mercury of water out there. So solving for the partial pressure of hydrogen, we get approximately 724.2 millimeters of mercury, and that's the pressure of hydrogen. But now we need to find how much hydrogen we have, and what is an equation we could use for that. So we are given pressure, right? We have the volume of the gas, and we have temperature. So we have P, V, and T. So that should ring a bell that we have, and then R is a constant, so we can solve for moles using that. But that requires our pressure to be in what unit? Atmospheres, right? So what's the conversion factor?
Divided by 760.
760 millimeters of mercury for every 1 atmosphere. That would give me 0.95289 atmospheres. All right. Have I lost anyone? Or are we all good? We're all good. Okay, cool. So, like I said, you could have done this using the PV equals nRT way, but because, well, I'll show you a different trick if they were asking for a different, if the question wasn't asking for grams of aluminum. If it was asking for something different. So now we need to find the moles using PV equals nRT. So N equals PV over RT. And we just add everything we've had in here. So 0.95289 atmospheres times the volume, which is 0.0358 liters. Remember, they gave it to us in milliliters, but we have to convert that to liters. And 0.0821 liters times atmospheres over moles times Kelvin. That's our ideal gas constant. And then we are going to put in the temperature in what unit? Kelvin, right? Because our calls for Kelvin, right? That's the units. So this has to be 27 plus 273 is going to be 300. Yeah, 300 Kelvin.
And this will give us the mole of nitrogen gas.
Yes, exactly. Because we are inputting the information of pressure of hydrogen gas, the volume of the hydrogen gas, and the temperature in which the hydrogen gas exists. So that'll give us the moles of hydrogen gas. What does that give us?
I got 0.00158.
So this is moles of H2. So let me break this over. So that's moles of H2, and now all we have to do is, and I'll bring it down here so we aren't so crushed for space. All right, now we just use what we always been doing is the mole to mole ratio, which is for every 3 moles of H2, 2 moles of aluminum were required to produce that amount. So we multiply that by 2/3. We'll get some number, but we can keep going on because we need not just the moles of aluminum, we need the molar mass of aluminum. So the molar mass of aluminum is 26.982. 26.982 grams. So what did y'all get as your final answer? This is gonna be grams. So, not too many grams of aluminum were required for this reaction. Are there any questions?
Another way.
Yeah, so if they had just asked for grams of how many grams of hydrogen gas were produced, you could have, instead of using ideal gas equation to get moles of hydrogen gas and then have to use the molar mass of hydrogen gas to in a separate part, you could have just used the I call it the density equation, but it's not really, you're not using any densities here. It's just MOV equals E times the molar mass over RT, where you can solve directly for M, the mass of the gas. So just because it's a question that's not asking about the density of gas or giving you the density of gas, you can always use this equation if you ever just need to find, if it's asking how many grams of the gas were produced, instead of going from PV equals nRT to N, and then N going from N to the mass using molar mass in a separate part, you can just use this equation and it'll get it all done in one step. So that's another trick we could use later down the line. Another trick that can go up your sleeves. All right. Let's do number 30. Have y'all learned about Graham's law of diffusion?
Probably in the video side.
That you haven't done? All right, that's okay. Would y'all want to skip that since y'all haven't learned, or do you want to go over it? All right, so you able to give a brief introduction to Graham?
Yeah.
Rich will give you all an introduction.
Right, as well.
That's what they call me.
And by day, you mean.
My bad if I sound like Pop Smoke, I don't know what's in the air today, but anyway, Graham's Law, right? Basically, it's called Graham's Law of diffusion or effusion. Like they're really the same thing. We use them, or they're not the same thing, but we use them like they have the same equation in one concept. Graham's Law of diffusion / effusion. If you want to know the difference, diffusion is when a gas moves like into a space, and then effusion is when it moves out of space. So that's a different thing. Or never mind, actually, diffusion is out, effusion's in. All right, so that's the basic point of that. So Graham's law, right? What Graham's law does is it basically, in simple terms, relates the rate a gas can diffuse and diffuse to the molar mass of the gas. So the rate and the molar mass. It's really all you need to know here. If you all had to guess, right? Would a gas with a larger molar mass, would it take more time to go into something or less time? More time, yeah, because it's like the analogy of like, if you're trying to fit like, if y'all have all seen Tom and Jerry, like Jerry the mouse, he can get into his like little hole very easily, but Tom the cat, he can't really get through, so he needs like more time in order to pass through that hole than Jerry does.
He also puts a double barrel shotgun inside the mold. That doesn't hurt this much.
I mean, we're just assuming that like it's his body only going through the hole, not any other personal objects. So Graham's law is basically this. It's a proportion of two rates of the gas to the square roots of their molar mass. So what it'll look like is something like this. The rate of gas A, this can be whatever you choose it to be. So in this case of this problem, either helium or fluorine. So rate A over rate B is the second gas, equals the square root. Remember, this is a square root. So is the square root of the molar mass of B over the molar mass of A. So if you talk about Graham's law, right, in the equation sense, this is what you use. So the rate of one gas over the rate of the other equals the square root of the molar mass of the gas, or the molar mass of the gas of the denominator over the gas of the numerator. It's important that you like mix them up in this way. So like another way you could write this is rate B over rate A equals the square root of the molar mass of A over the molar mass of B. It's just that whatever you put on the denominator for your rate has to be in the numerator for your molar mass. So that's basically what Graham's law is. And something else I like to do, right, in these types of problems is depending on what I'm solving for, like say for example, I'm solving for the rate, I'll see whether or not the answer actually makes sense. So in other words, as y'all said, something with a large molar mass, so it would take more time to diffuse. And then the same thing, something with less molar mass would take less time to diffuse. That's the basic idea. Any questions over any of that? All right, want to practice? Okay, so let's do number 30. At a given pressure and temperature, it takes 4.85 minutes for a 1.5 liter sample of helium to effuse through a membrane. How long does it take for 1.5 liters of fluorine to effuse under the same conditions? So, what do y'all think? What should we do first? Yeah, find the rates. Or I should have asked this first. Well, what are we trying to look? Yeah, we're looking for the rate of effusion of fluorine specifically. So rate of fluorine. That's what we're looking for. Do y'all want my the fluorine to be rate A or rate B?
A, or no, B, because that's the second one.
B, sure, okay. So rate A, so I'm gonna erase this bottom part here. So rate A over rate B equals the square root of molar mass of B over the molar mass of A. So the question is, we don't have rate, do we? We have time. How do we get from a time to a rate?
Oh, divide the volume by.
Volume by time?
Okay, never mind.
Or, it was a good guess, but there's actually a way, simpler way to do this. For those of y'all in math class, right? For those like who remember math and like physics, what is a rate? Like, what do you define as? Something over time, exactly. So if my rate equals something over time, so like 1 over the time, my time just equals 1 over the rate. Or you see how I rearranged it there? I just multiplied both sides here. So we can really substitute however we want, but in this case, we're looking for the rate, so we'll use the top. So our rate here equals 1 over 4.85 minutes. There's minutes, right, in the problem. Should we convert that to seconds? All right, who says yes? Who says no? Who's not sure? The truth of the matter is, you don't need to convert it to seconds.
Because it takes longer.
Whoa, yes, but another reason is it's not really needed for the problem. So if your rate is in minutes, it's completely fine, as long as like both of your rates are in minutes. So you can't have like 1 in minutes, 1 in seconds. Y'all get what I'm trying to say?
Plus it's 8.85 minutes, and you have to, calculate it in 60 seconds.
Yeah, I mean, it does take more time, but for the purposes of this, just know that you don't always have to convert to seconds if you're not asked. So we're gonna do that. So 1 over 4.85 minutes. So what is our rate gonna be?
Is it 1 or is it 1.5?
So generally, right, here's how we depict rates. So the rate, so time, right, or let's do it this way. Here's how I like to do it. Rate is equal to speed, right? Speed is equal to what? Distance over time. So it's some number here over time. So in this case, really what I'm trying to say is time is the inverse of rate. So you just do 1 over it. So
You wrote 1 and then it probably states 1.5.
that's just to show that like the volume samples are the same. Because like, say for example, you had like 1.5 liters of helium and then like 3 liters of fluorine. Of course, it's going to take the 3 liters more time because it's more like a greater amount. Well, the reason why the 1.5 is there, the 1.5 is extra information. Yeah.
So you don't really have to-
He's asking about your converter for 1.
Yeah, that's what I'm trying to explain.
Oh.
Like the 1.5 is extra information. So in this case, like the 1.5 here, this could be any number, like 5, 6, 8, whatever. What I'm trying to show is that the 1.5 just shows that both the samples are equal, so we can compare their rates. Because like if you were to have different volumes, it's like comparing apples to oranges. Does that make sense?
Yeah, at no point when you're using Ramp-Up is the volume going to come into question when you're doing a problem. Like for the most part, you should always have if it's 1.5 volumes of helium, and then you want to look at fluorine, it's going to be 1.5 volumes. You're never going to have 2 different volumes. So because they're always going to be the same, they don't matter. So it's just extra information, like Ruben said.
So here I'm gonna change up my rate A and rate B because we actually know the gases we're looking for. So the rate of helium over the rate of fluorine equals the square root of the molar mass of fluorine over the molar mass of helium. So now we've established rate is equal to 1 over time. If you take nothing away from this problem, take away that. Rate is equal to 1 over time. Time is the inverse of rate is the inverse of time, and vice versa. So to get the rate of helium, you have to do 1 over 4.85 minutes, which is what? Like 1 divided by 4.85, what is that?
20618.
0.20618. Right, 0.20618. And this is, technically this is volume here that we're diffusing, so I'm gonna put it in units of volumes per minute. V per minute. The rate is always like, as somebody said, per unit time. So since we're dealing with minutes here, it's something per minute.
Or.
Yes. This is for helium. So we have 0.20618 volumes per minute of helium over the rate of fluorine, which we don't know yet, equals the square root. And now, y'all know the molar mass, right? You just look on the periodic table for this. So what is the molar mass of F2? 38. Yeah, about 38, I'll say 38. So 38 over, what's the molar mass of helium?
Hydrogen one, helium is
4.0066.
All right, I'll just use 4. So 4.0026. All right. So now we have all of our information. All we need to do now is solve for the rate of fluorine. Let's clean this up a little bit. So 0.20618 over the rate of F2 is going to be equal to some number. It's just a number on the right side, right? Because that's what we're doing here. So
what's the square root of 9.5? If you divide it now.
well, that's nice to know, but square root of 9.5. But the thing is, we have a calculator. We can use calculators in this class, so we can get down to the exact decimal. So what is that?
3.0822.
3.0822. And that is with the square root?
Yes.
All right, 3.0822. Sorry, I was just trying to make sure. All right, so now here we're going to solve for the rate of fluorine. The rate of fluorine is going to be equal to 0.20618 over 3.0822. And we get our rate of fluorine being equal to what?
So what are the units for?
It's the same thing. Volumes per. Oh wait, no, it's not. I'll let.
That would have no units because it's molar mass over molar mass. So that would just end up being like a ratio, not a number. Because remember the square root was square root of molar mass of 1 over molar mass of 2. So just grams per mole over grams per mole cancels out.
So rate of fusion is just a
Hmm?
rate of fusion is just a number.
What was that?
Rate of fusion is just gonna be a number then.
Rate of fusion is gonna be a number per minute, the unit time. So because this 3.0822 has no units, that actually works out perfect for us because we don't want grams per mole in our final answer. We want per minute time, which in this case, because we started with minutes, it's gonna be per minute. The final number will be with units of inverse minutes. But you see why that there's no more grams per mole, right? Because they canceled out up there.
That's right, then 38. So this is grams per mole, and then same thing here, 4 grams per mole.
Yeah, some people like our units, Rich.
All right.
Yeah, so the 3.08 has no units anymore, but the 0.20618 would still have units of inverse minutes.
Okay.
You just didn't write it down.
All right, what is our fluorine rate?
0.06.
0.0669 minutes to the -1, or volume over minutes. Yeah.
And I assume when we're like putting this into the calculator, we solve like the significant figures of the volume given.
Because you didn't use it in your calculations.
Okay.
You wouldn't use it. Alright, because your sick fees should only come from the things you utilize in your calculation.
But probably a longer number than everything.
Just one extra sick day.
Yeah, so if we're taking into account sig figs, the final answer should have 3 sig figs, which in this case, 0.0669.
Yeah, I'm not sure how his problems have been on the active recently, but I remember him always saying that, right, do it to this many decimal places. And if that's.
His actually, they're like, yeah, he guys have things.
Yeah, so if it's on the iPhone, you'll probably play the numbers.
That's it's follow directions.
Yes.
It's on all this.
Yeah.
All right. .0669. But this is a rate, right? This is a rate. Does it ask for rate in our problem?
It takes how long?
Yeah. It's how long, a rate, or a time?
If someone asks you, how long until you get to my house? Are you gonna tell them the rate that you're going in terms of how fast you're driving? Or are you gonna say, I'm gonna be there in 25 minutes? Right, so when it says how long will it take for the fluorine to infuse, you shouldn't tell the person, oh, it's 0.00 or 0.0669 per minute. It doesn't make sense, right? So we want to tell the person how long it'll take the fluorine to infuse. So how would we get from rate to time? Rate divided by rate. Yeah, so rate equals 1 over time, right? So that means time equals 1 over rate.
Yep.
Right?
Time equals 1 over rate. So we do 1 over 0.0669. And then if you do that, you should get a rate of approximately 14, or sorry, not a rate, a time of approximately 14.96 minutes.
And it makes sense because this number here is in units of per minute. So if minutes in the denominator and it's that whole number's in the denominator, then it goes to the numerator, right? You able to write that?
This is minutes to the -1 technically. So to move it to the top, you'd just move it up. So it's.
Yeah.
Does this answer make sense? Why does it make sense?
Fluorine is better than helium, but that's longer for good.
Exactly. Fluorine's heavier, so it takes longer to infuse, which according to the math is indeed what we get. And if we look at it, it's nearly like 3 times as long.
Let me go on number 31. It's been a minute since I've associated myself with Graham.
No one wants to associate himself with some shady individual with chemistry, so we'll do it better.
All right, number 31. Example of an unknown gas, effuses. Effuses should be a trigger word for you. All right. When you think of effuses, when you hear effuses or diffuses, there should be, your mind should already start compiling everything that relates to Graham's law. Okay. So the 2 equations that we are going to be using are most likely going to be rate of A over rate of B equals the square root. And actually, I don't know why I'm writing. Square root of the molar mass of B over molar mass A. All right, so that's one equation that should come to your mind as soon as you see the word fuses or diffuses. The other one is what? Yeah, rate equals 1 divided by the time it takes for that gas, right? So trigger words cause us to think of some equations, all right?
We don't have to worry about volume. Because it says equal volume, so,
What was that?
but we don't have to worry about volume, because it says equal volume.
Yeah, exactly. So that just goes to show they didn't give us any volume numbers in this problem, so it's just extra information that they do give you volume. All right. So an equal volume of H2 in the same apparatus under the same condition effuses, keyword reaffirms that we're buddies Graham's law at 2.42 minutes. What is the molar mass of the unknown gas? Interesting. So we're looking for the molar mass this time. So we're gonna be isolating one of these variables on the right side of the equation. So let's go ahead and let's work with the variables before we plug in numbers like Rich did, because it gets really ugly really quick, as you can see.
Well, we first look at the unknown side is heavier than, hydrogen.
Yeah, we do know that, but let's take it one step at a time, all right? So we need to isolate, we're looking for the molar mass of one of the gases. Right? So do we want that to be A or B? Yeah, the unknown. So it doesn't matter. Mathematically, you can get to it either way. But it's easier to solve for the molar mass of B in terms of doing the algebra and getting to that equation, because you square both sides and you would get rate A over, rate B squared, or not squared equals this part here. Molar mass of B over molar mass of A. And then we just multiply it, molar mass of A to both sides. So I encourage you, next time solve for molar mass of A, it's just a little bit more algebra you have to do. Yeah. Okay. So our final equation is going to be rate A over rate B squared times the molar mass of A. So let's make molar mass, or let's make B our unknown, okay? Because we just solved for that, and that's what we're looking for. Is everyone with me so far? All we did so far was rearrange the equation to solve for one of the molar masses, because that's what we're being asked to solve for, the molar mass of the unknown gas. Now we just plug in all of the information. So let's start with rate A. We said B is going to be our unknown. So rate A is for hydrogen, right? So the rate for hydrogen is equal to the 1 over the time it takes, which in this case is 1 over 2.42 minutes. 2.42 minutes. Which gives us 413, and this is going to be in units of minutes inverse, right? Minutes inverse minutes. All right, now we need to solve for, and this was rate A. Now we need to solve for the rate of the unknown gas, which is going to be
0.0.
yeah, so which is rate B equals the 1 over time it takes for B, which is equal to 1 over 11.1 minutes, which equals 0.090 inverse minutes. So our pieces of information are specifically all these here, right? And we know that the molar mass of H2 is just 2 grams per mole. So we can see that all this information fits pretty nicely where it's going to go. So the molar mass of hydrogen goes there. The molar mass of A is going to go here. And then the last one will go down here. So it's important that you don't mix those up. So now we just plug and chug, as they say. So 0.413 inverse minutes divided by 0.090 inverse minutes squared times 2 grams per mole. And this equals the molar mass of our unknown. So as we see, we can cancel out inverse minutes cancels out and we're left with grams per mole, which is what we need in terms of our units, because we're solving for a molar mass. And when you do this, you should get a molar mass of the unknown gas, which of 42.2 grams per mole. How do y'all feel about that?
What if I ask you to, excuse me, what if I ask you to identify the gas? Yep, see which one's closest to.
Yeah, the only thing is it's hard to identify a gas when they don't tell you like maybe what group it's in or something. Just because there's so many possible combinations of that can be gases. So I think there's a problem in here maybe that says the unknown noble gas, and you know to look at the noble gas group, right? So, or maybe it'll say diatomic gas, and you know there's only certain diatomic elements, and you know them molar mass. Yeah.
Did you flip the rates around based off it?
Did I flip the rates around?
Yeah.
A over,
A supposed to be helium.
we don't have helium in this one.
Or sorry, hydrogen.
Yeah, A was, yeah, because rate A equals 1/2.42, which is equal to 0.413 per minute.
Yeah.
And we put A in the numerator, so I put 0.413 in the numerator over here. Or where do you see my mistake?
I think I messed up because I said, okay, yeah, I said the rate was 1.1, not the unknown gas 1.1.
Oh, I see.
Yeah.
Yeah, so did you get the same answer?
No, technically more out.
Oh, okay.
That's what I do.
Okay, yeah. So this equation gets tricky just because it has A over B on one side and B over A on the other side. So you cannot forget that those in the initial equation on the top left, it's A over B square root B over A. So practice with this equation until you start to remember that, or you can just remember that.
If you were to put, if you were to flip them, and then you would divide the molar mass, then you get the same answer.
If you were to flip 0.09 over,
Yeah.
no, you wouldn't. Just, I mean, just flipping that alone, you're definitely gonna get a different answer, because 0.09 divided by 0.41 is different than 0.41 divided by.
You have to put like your no into the rate, which was it?
Oh, you don't necessarily. Wait, so what were you saying? Are you saying that
Instead of,
choosing, yeah,
0.413 over 0.09, flipped it, but then you divide it by the molar mass instead of multiplying. It's all for the.
so are you saying, because I originally identified, I established that I was gonna use B as my unknown. Are you saying that I would use A as my unknown? So, yeah, you could have still got it, that way. It's just a little bit more math that has to be done, because you gotta divide this term. If we're isolating for A, then you have to divide this term over. And then you get a big fraction in the denominator, and then you multiply that one over. So your final equation would be MMB over rate A over rate B squared equals A. So it's doable. That would be your new equation that you're using. You would be using this equation rather than this one here. So it's the same thing. You'll get the same answer for sure. It'll be a little iffy if you put it in your calculator. I don't know. So it's up to y'all, however you want to do it. Any other questions? There's always one of these problems on the test. What else is there on the test all the time?
I mean, your usual individual gas laws, like combined, Boyle's, Charles, Avogadro's, ideal gas.
Oh, yeah, there's also some of these problems for sure, like the density of gas.
Graham's law, there's always like one question on each of those at least. And then sometimes there's a question. It's a kind of an idea that he hits on a couple times, maybe if you don't have him as your professor. But it's like question 32, about gases behaving, how they behave when they're further away from their boiling point. In terms of how ideal they be.
Not ideal.
For what?
I mean, if they're further away from their ideal boiling point,
What do you mean their ideal boiling point?
what says behave more ideally at 50 or 20 Celsius, where behave more ideally at 20 Celsius as opposed to the boiling point.
No, because when closer to its boiling point, it's more likely to become a liquid. So the further you are from your boiling point, the more characteristics of a gas you have.
Oh, yeah, because either heat cell incredibly or freezes, that's all, okay.
Yeah. Yeah, so that's another idea, is that gases behave more like an ideal gas when they're further away from their boiling point, in the positive direction. Not if they're a solid, obviously they're not gonna be behaving like a gas. But yeah, so. Are there any other questions?
I'm David,
Been good, thanks.
thank you.
Any other questions related to the course? Yeah.